Hello everyone, welcome to the session 2. So we're going to continue with the chapter 1 of the number theory by Maryam Mirzakhani. So we were doing the division chapter, so I believe we stopped at the theorem that we had. So now let's see a problem, how we can use part of the theorem we saw to solve some problems. So the first problem, so suppose that we have suppose A and B are two integers. We want to, and we also know that 11 divides 2a minus 3b. So now we want to prove that 11 also divides 7a minus 5b. So in this one, we just have two assumptions. A and B are just integers. We have this assumption that 11 divides 2a minus 3b, or 2a minus 3b is a multiple of 11, or the remainder of their division is going to be 0. So now we want to prove this statement that 11 also divides 7a minus 3b. So you can pause the video to try to figure it out for yourself, and then we were going to solve it. Also, as a hint, we're going to use, like, I can write down the hints, because usually when we see some problems from now on, we have to try to be innovative. It's not like always we're going to see right away through the solution as a systematic way of solving it. Sometimes we have to just write down, try different things out and see which one works. So for a hint, the theorem, the part of the theorem we're going to use from last session to prove this one is the one that we had this part of the theorem that was saying that if we have number C which divides A, and also we have C which divides B, then we can conclude that for any x and y that also are integers. So when you see that inverse like A, this is another symbol to says like any x and A over the integer like domain. So you can just randomly choose two integers. And if we have these two assumptions, we can also know that C gonna divide any linear combination of those two numbers. So A and B, you can choose another two integers and create any combination of them linear. And then we know C divides them as well. So this is what we're going to use for this problem. Let's see how it works. Okay, so let me change colors here. Okay, so when we have, let's work with this assumption and see what else we can just like try to figure out based on our assumption here and write it in different versions, because we can see that eventually we have to go from these coefficients or these numbers like 2 and minus 3 somehow to 7 and minus 5. So we have to probably add or like add some terms that we are allowed to do, but let's see how we can do it. So we already know that 11 divides 2a minus 3b, or also 2a minus 3b is a multiple of 11. So what I can do is multiply this number by any integer, and we still know that the 11 gonna divide that number. For example, if you know that 6 is dividing 12, because 12 is a multiple of 6, I can get that 12 and even multiply it to make it a bigger number, like by 5 to become like 60, and still I gonna know that 6 divides that 60, right? So in this case, we can choose a multiple of 5, and I can say, okay, 11 actually divides 5 times this 2a minus 3b. And if I just like use the distributive like community to apply this multiplication, we're gonna have 11 divides 10a minus 15b. Also, so let's have this like a store here. Also, we already can know that 11 divides 11a as well, because 11a simply and intuitively is obvious that it's a multiple of 11, because you can just find an a and multiply it by this 11 to get this original number, so the remainder of this division gonna be 0. And when we have like this, let me choose it as double star, I can look at this one and this one is star, and in their combination, if I add them together like the right size, when you have a number which is a multiple of 11 and another number which is a multiple of 11, one type of their linear combination is going to be that if I simply just have the multipliers as 1, so meaning like simply summing them together. So now here, if I do the right parts, I can get to this expression that I have 11 actually divides, it's gonna be 21a, because I have 10a here plus that 11a is gonna give me 21a minus 15b. So let's call this the first statement. We're gonna use another statement to get finally to what we want. Okay, let me clean up a little bit, because we already have the assumption. I just leave the assumption here so we know that's the assumption and that's the final thing. Let me also clean up the hint. We're gonna rewrite this. So this was our assumption, and what the verdict we want to finally prove is this one. Let me rewrite it here. Okay, I clean this part as well, because now we got to this first conclusion. That's what we need for that. Okay, now we're gonna use another multiplier. So let's see, we already have 11 2a minus 3b. In the first one, I multiplied this by 5, and then we had 11 also divides 11a, added them together, and we got to this one. So now for the next part, I can use the same one, but this time we're gonna use the multiplier of 7. So these are the innovative numbers sometimes you have to work out. And then I show like another way, kind of systematically, we can find these numbers, but for now, let's see. We have 11 divides this, so what I can do is multiply this number by 7 as well and say that this number also is gonna be divided by 11. So if I use the distributive community here, 7 times 2a gonna give me 14a, and 7 times 3 gonna give me minus 21b. Now instead of using the 11 divides 11a, what I can use is, like, now if I consider this as my star, I also can write that 11 actually divides 11b this time, because also 11b is simply just 11 times b, so they're multiple. And the division of this by that gives you an actual integer and with the remainder of 0. So now what I can do from this and that is, again, add them together, because one linear combination of these two numbers, which are both divided by 11, is just sum them together with multiplier of 1, like 1 times this number plus 1 times this number. So if we add them together, we can write it as 11 divides, we have 14a, and then if I add 11 to minus 21, it's going to give me minus 10b. So now I call this my second expression. So now let's look and see how this 1 and 2 can help me to get to the verdict. So we just played around with a bunch of terms to get to another version of a number that is also, we are sure, based on our assumption that it's divisible by 11. So now if we look at these two, I can simply, again, in this case, instead of summing them together, I can subtract this number. So if you recall again from our hint, when we had C divides A and C divides B, we could have said that C divides ax plus by, which this x and y were just randomly chosen from any integer, so any linear combination. So in this case, I can choose x and y, let's say respectively for the first one, like kind of 1, and then other one -1, which leaves us as kind of their subtraction or their difference. So now using that, I can say, okay, 11, if I use it as, let's say, we subtract the second one from the first one. So I have 21a minus 14a, which leaves us with 7a. And then I have minus 15b minus 10b or plus 10b. So minus 15b plus 10b is going to leave us with minus 5b. So now if we look, this was the verdict that we wanted to actually prove. So 7a minus 5b. So just using this assumption and using the hint with bunch of like different linear combination of these like terms, we got to this verdict as well. So yeah, this is the part that sometimes, yeah, it might take a little bit time. You have to try different things out because the numbers we use, it was like the 5 multiplier, we use a 7 multiplier, and also the facts that 11 divides 11a and b, and then we mix them all together to finally get to this one. So let's see the next part, which is another theorem. And this theorem is about the division algorithm, which gives us so much flexibility to start like solving some actual problems as well. So this might come like intuitive, but let's go through it and we can prove it as well. So we suppose that we have a and b, which are two integers, and we know that b is not 0. Because we want to divide a by b and see what the quotient and remainder are, and then we know that we can divide by 0. So that's why this b is not 0 is part of the assumption. Then we have unique integers such as q and r, which are respectively called like quotient and remainder, like as the abbreviation of them, which we have this relationship. So a equals b multiplied by that q or quotient plus r. So it's kind of showing that if you divide a by b, you're going to have q integer parts, and then the r, which is also remainder of that division, also as an integer. And then we have to have this relationship for the remainder as well, that the remainder always should be positive or at 0 at the least. We cannot have a remainder negative. And then the size of this remainder is always going to be less than the absolute value of b, because b can be negative as well, but when we consider the value of it, it's just going to be less than it. So let's prove this and then see how we can use it. So first, for like considering like we have such a like q and r, because as you can see that in our verdict we have unique integers, so meaning that this q and r, when we do the division properly, you have to just get to a distinct like solution. You can't have divisions like done by two different people and then two different results, right? So one is going to be wrong. So first, for proving this like theorem, first we're going to go and find a q and r, at least one pair of them that they satisfy this like condition and relation that we have, and then we prove that they also are unique, and you cannot have multiple like pairs of q and r or quotient and remainder that satisfy this at the same time, and they're different than each other. So for proving this, we have to first consider this sequence of numbers. So imagine we have like 0 here, and then the next like number that I'm choosing here, and there's a reason that we want to do that, but let's work with this. So we are moving steps by absolute value of b, and I'm considering those numbers as a sequence of numbers. So we have 0, we have absolute value of b, the next one going to be 2 absolute value of b, 3 absolute value of b, and so forth. It's just like going to continue. And in the negative direction, we also have the same step size, so absolute value. So from 0, it's going to become minus absolute value of b, minus 2 absolute value of b, and so forth as well. So now we know that because these are just numbers and they're covering the whole like range of numbers. So if I'm just looking at a, and we are just having here absolute value of b, A has to fall somewhere in between these numbers, right? We don't know exactly where, but it has to like fall between two consecutive um, numbers in the sequence. So it might be exactly like landing on this, like for example, absolute value of b, it might be one to the right of it or anywhere between these two numbers, or land again on two times like absolute value of b, or anywhere in between. But at some point we know that it's gonna like land somewhere between two of these consecutive like elements, right? So let's just like wherever it falls, we consider then we can find, or there exists a q which belongs to the integer numbers, that I can say, okay, a is between these two consecutive elements, right? And what are those consecutive elements? One of them is that we don't know where that q is, but for now we know it's just something multiplied by absolute value of b, because these numbers are just like absolute value of b with a multiplier or a coefficient behind them, either positive or negative. We don't care about it, so it's going to be an integer, but we know it's something like q times absolute value of b. And the next number in the consecutive like term is going to be in the series q plus 1 absolute value of b. So we know at least there is such a q because a has to fall somewhere between two of these, right? So now let's define r, because now we know there is a q like this, and then we have to show that this satisfies this like condition, right? But now we can also define r. When you see like a triangle on top of the equation, it means we are defining r as this, because r is a variable and we are saying we are defining such as r equals to a minus q absolute value of b. So if we define it in such a way, let's see first how can I get to this condition from this inequality that we have here. We know in the inequalities I can either add or subtract the same value from all sides of the inequality, or we can multiply all sides by a positive number, or if we multiply all sides by negative number, then we have to be careful to change the direction of inequalities, but we can do all those operations, right? So now in this case, I just gonna subtract q times absolute value of b from all sides. So what we are doing is, if I write it on top, I'm minusing q absolute value b from all sides. So now what happens? Q absolute value of b minus q absolute value of b are going to leave me 0 in the most left hand side of the inequality. Then we have greater than or equal. Then we have a minus q absolute value of b. And then we defined it ourselves that, oh, we want to call that r, right? And then less than. And then q plus 1 absolute value of b. If we take q absolute value of b away, we are just left with 1 absolute value of b. So now we can see that because of we knew that a would fall somewhere in between, we have a q, at least in integers, that this a falls between those two consecutive elements. And then we can define r in this way, which leaves us the value of r between 0 and absolute value of b. So now if we look at it, this is what we wanted here, right? So now if I can prove this part as well, that now a is actually bq plus r, or there exists some integer that holds like relationship like that, then we are fine. So now we have two cases, because b can be positive or negative, right? So if b is positive, let's see, so this relationship always gonna stay here, because we are like even have absolute value of b. I don't need to change it, and like in this case say, okay, if b is greater than 0, absolute value of b gonna be b, which is correct. And then if b is negative, this absolute value gonna be negative b. So there is still like the same thing. But let's see what happens to the a. So in the case, because r is defined as this, if b is greater than 0, r is just going to be a minus, and absolute value of b is going to be b itself, so minus q b, and then I can send this qb to the other side of the equation, so a gonna become bq plus r. So a has been written as like b multiplied by another integer plus that r, and r is also satisfying this. So that's for the first case that we have both conditions. And for the second case, because b is less than 0, so absolute value of b is going to be a negative b. So r is actually going to be a plus, because this is going to give us a negative b, and then bq. So now if I send this bq to the other side of the equation, it's going to become a equals minus bq plus r. Instead of minus bq, I lend that minus to q, so it can become b multiplied by minus q plus r. We still have this relationship for r, so r is satisfying that. And then if you look at this, I still found an integer, because in this case, if q is an integer, minus q is an integer, just inversing the sign. So I found an integer that is still getting multiplied by b and get it added by that remainder, which satisfies this condition, as giving us the a. So in both cases, we have that quotient and remainder that satisfy both of this, right? So now that we've proven that there are such exist like such integers, we have to prove they're unique as well, and they're not like different pairs exist there. So what we can do in this is, we first gonna assume that there are different like pairs, and then we come to a contradiction, and then realize that there can't be more than like one distinct pair for that r and q, and then that proves it. So now let me write it again. So imagine we found the Q and R in this. Is it running out? The ink? No, we're fine for now. Imagine we have that and we found R and Q and such, but then let's assume that we found another like R prime and Q prime that actually they also satisfy this. So we have like two pairs of these numbers, right? So now what we can do is, because a equals both of them at the same time, so let's just write them as equal to each other. bq plus r gonna be bq prime plus r prime, right? If I now send, let me see, yeah, we can send them to one side, and then this becomes, let's say, bq minus bq prime equals to minus r plus r prime, or r prime minus r. So now if I take the absolute value of both sides, we can write it as absolute value of b times q minus q prime, absolute value, because the negative doesn't matter in absolute value, we can write it as r minus r prime rather than r prime minus r, right? Okay, so what happens here is, we already have this part as well, that r is between that and r prime is between that. So from just these two, we can be sure that r minus r prime, the absolute value, because these numbers individually are less than the absolute value of b and greater than 0, so their subtraction for sure going to be less than absolute value of b, because it's less than the whole interval, so it still doesn't matter. If two numbers are getting chosen between, for example, 0 and 12, their difference for sure is less than 12, which is the maximum number of that interval, right? So we have this as well, but now look at this equation. I can, because absolute value is just getting rid of that negative value. Absolute value of two numbers getting multiplied by each other is just absolute value of each of them. So I can just rewrite this as absolute value of b multiplied absolute value of q minus q prime equals to absolute value of r minus r prime. And from here, we know r minus r prime, actually absolute value is less than b. So now if you look at this left-hand side, absolute value of b multiplied by this absolute value is less than the absolute value of b. So what it tells us is absolute value of q minus q prime is actually less than 1, right? Because it's making like you can kind of like divide both sides of this by absolute value of b, because it's a positive number. We don't need to change the direction of inequality, so we get to this like part that the absolute value of q minus q prime is less than 1. And we know q and q prime, they're both integers, right? So when the absolute value of their difference is less than 1, the only thing that it means is like absolute value of them is actually 0, and then we have an absolute value equal to 0, it actually means that the number inside is 0, or actually q minus q prime is 0, or q actually is q prime. And then q is actually q prime, so bq is bq prime, and these two cancel out, and r actually is r prime. So we prove that these two apparently different like pairs that we have for quotient and remainder, they're exactly the same. That's why there's just one set or one unique integer such as q and r. And when we have such other things, they're all exactly the same, so we are not finding different numbers. So now we prove that they're also like unique as well. So this was a mouthful, but for something that kind of might be intuitive and very easy to understand, that this is how we do the division, right? You divide a number, you get the maximum integer amount that you're allowed, and then there's a remainder. Might be 0 or might not be, but it for sure should be less than the number you're dividing with, because you can't get more than that units if you don't have enough units, right? But now we are extending it to a case that b can also be negative, because so far in like high school, what we've seen is usually that we are just working with a and b, that they're both like positive integers, and we're doing the regular division. In this case, this applies to the negative numbers as well, but the conditions stay the same as well. So now let's see how it helps us in solving some other problems as well. Let me check the time as well to see how long we're running. I don't want these chapter videos to become too long, so if it gets around an hour or so, we can cut it, so we continue it in the next one. But let me check the time. 27 minutes in. Okay, very good. Okay, now let's see the next problem. We want to prove that a square of any odd number is of the form, or can be written in this form, is of the form 8k plus 1. Okay, so let's see how we can use that division algorithm, excuse me, that we just saw, how we can help it to solve this one. So now we are working with odd numbers, and when we are talking about odd or even numbers, we are considering dividing those numbers by 2, and if the remainder is 0, we call that number even number. And if the remainder of that division is 1, we call them odd, like 3, 5, 7, so on. So now let's see that from the same like a, b, q plus r that we had, now if we're considering division by 2, it means that we're considering these two, right? So when we have b equals to 2, our number can either be something like 2q plus r. And what is our r? R is the remainder, which should be either greater than or equal to 0, less than absolute value of b, which is 2. So because r is an integer and is bounded to 0 included and 2 not included, it means we have only two cases, right? R either going to be 0 or r going to be 1. In the case r is 0, we call that a becomes 2q, and we call a as even number. So in this case, we have r0, and when r is 1, a becomes 2q plus 1, and we call this number odd. So now they want us to prove that when we are taking a square of any odd number, which is kind of the format 2q plus 1, that number is going to be of the form like 8k plus 1, which meaning like this has not been set here, but we are imagining about k is also an integer when we are talking about 8k plus 1. So that the square of that number eventually can be written as 8 multiplied by an integer plus 1. So let me just close the terrace, I guess. I don't want the outside environment sound get captured in the song. Yeah, one sec, please. All right, so now we have to work with these odd numbers, right? 2q plus 1. But since working with k is easier to write it than q, let's work with 2k plus 1. So instead of 2q plus 1, it doesn't matter. This can be any integer or any symbol, right? So let's work with the 2k and call that a is kind of 2k plus 1, odd number. So now let's see what happens when we're trying to take a square of this number. a2 becomes 2k plus 1 to the power of 2, right? So from the first identity equation, we know when we have a plus b to the power of 2, it becomes a squared 2ab and then b squared. So a squared is the first term squared, 2k squared going to become 4k squared. Then we have twice their multiplication. Their multiplication is 2k, twice is going to become 4k. And 1 to the power of 2 going to become 1. So now this is the square of any odd number that kind of has this form, and we are claiming that we can write this number in this form. Let's see how we can do it. So what I can do is like first look at these two terms here, because this is odd, we can't do anything, but these two terms have like 4k in common, right? What I can do is factor that 4k out, and the first term leaves me with just a k, and the second term just leaves us with a 1. And then the remaining 1 is going to stay there. So now we want to focus on this part of the first term that has k times k plus 1. Because k times k plus 1, there are exactly two consecutive integers, right? For example, if k is 5, it's going to be 5 and 6. Or like it's going to be 7 and 8, right? All the consecutive numbers. So what happens between consecutive numbers is like if I use this as a scratch pad, we have k times k plus 1. So either k is a odd number. In that case, k plus 1, because it's the next number, it's going to be an even number. Or it's the other way around. K is going to be an even number, and then the next number is going to be odd number. So either way, their multiplication consists of one even number at least, or exactly one even number, right? And one odd number. So in this case, it means that this k times k plus 1, we can find, or there exists, let's say, another m, which is an integer, and then I can write this multiplication as 2m. Because if I know their multiplication is a even number, every even number can be written as a form of 2k or 2m or 2n, and we can find, or there exists such integer, right? So now if I replace this k and times k plus 1 with a 2m, and m is an integer, I'm gonna have 4 times this 2m and then plus 1. So 4 times 2, I'm gonna give us 8m, and then we have a plus 1. So now we prove that the square of an odd number is gonna be of the form of 8 times an integer, because m, it can be any integer, right? Times an integer plus 1, which is what we wanted to prove, because we are talking about forms like this k and m just are considered symbol of integers. So we prove just the form is there, that we have the 8 multiplied by integer plus 1. And it also tells us that this number, if we divide it by 8, what's going to be the remainder? when it's of the form 8k plus 1 or 8n plus 1, the remainder going to be 1 because this 8k can be easily divided or is divisible by that 8, and then it just like leaves us with this one. So that's one way of like how we use that division algorithm to consider odd numbers in the form of 2k plus 1, and then go ahead and prove that their score is going to be a form of like a multiple of 8 plus 1. And then there is a conclusion written after this problem. There is no proof for it, so I'm gonna assume that that was related to the problem we just solved and the conclusion there, and we use that to like just justify why this conclusion was written after this. So the conclusion right after this problem is conclusion 1.6, that any number of the form just once, like we just have 1, 1, 1 all the way once, and we can consider we mean like k ones, and this k is greater than 2. So any number of this form is not, or like can't be, a perfect square. Means that if you take the square root of this number, it's not going to give you a perfect integer. It's going to be an integer with decimal points. So if you want to consider that, because the previous problem was telling us any square of odd number can be written in the form of 8k plus 1. So first, if we look at this is an odd number because we know we have all ones, and if we look at the excuse me, ones units, we have one which like tells us this numbers is an odd number. So if it's an odd number and it's a perfect square, so then it means that it should be of the form of 8k plus 1, right? Because a even number cannot get squared and produce an odd number for us. So for sure, if there is an odd number that can get squared and provide us with this number, and this number should be of the form 8k plus 1. And then simply if we can prove that this number is not of the form 8k plus 1 or 8n plus 1, then we know that this is not a perfect square. And then for doing that, I guess we have to know how to divide this number by 8, right? So one thing that we can write this number as, this number is gonna be whatever ones that we have, and let's consider this separation. So instead of like k ones that I had here, now I'm gonna have k minus 3. And then there is one case that we jump, so we have to prove that manually as well, because when I separate this number as like I separate the last 3 and write this number as this, I'm assuming that k is greater than 3 as well to have at least one left here. If there is a case that exactly k is 3, it means we have to check whether 111 is a perfect square or not, which is in this case we know it's not, because 10 to the power of 2 gives us 100, and then next number 11 to the power of 2 is going to be 121, so 111 is between, so it's going to be 10. If we take the square root, it's going to be 10 point something, so this number already is. So now that we check that, we can assume like k is already greater than 3, and this separation makes sense for us. So when we have this number also here can be written as 1000 multiplied by this k minus 3 ones that we have, and then plus this number. So we know already 1000 is a multiple of 8, right? Because if we divide 1000 by 8, it gives us 125, right? So this number is already kind of, I can write it as 8m, like in the form of a multiple of 8, and then multiplied by another number, doesn't matter, let's call this n. So this whole point here, this term here, can be kind of written as just an 8k. So this part is fine. But then we have 111 remaining. Let's see what's 111 when we divide it by 8, how much remainder we get. 1, and then we have 31, it's going to be 3, 24, and then we have 7, right? So now this 111 can be also written as 8 multiplied 13 plus that 7. Again, this part is both their multiples of 8. 8 times 13, 8 times k. I can simply write them as, let's say, 8 a. Big A, doesn't matter, plus 7. So now we prove that this number can be written of a form of a multiple 8 plus 7, but not a multiple of 8 plus 1, because that's not going to be possible, or telling us that this number's remainder by 8 when you divide it is going to give us a remainder of 7, not a remainder of 1. So that's what it seems rational to me if we jump into this conclusion after that question. So we have to use this like 8k plus form, but there might be other ways to just show that that number cannot be a perfect square. So let me again check time. 41 minutes. Okay. So now let's see the next problem, which is actually, yes, the last problem of the chapter. So we can go through this and finish the chapter. Then we have some complementary, I guess, practice problems at the end of the chapter, and then we're going to cover them in just a separate video so we can just see the problems by themselves rather than some of the theories. But I believe there might be some like proving problems there as well, something like that. Yeah. So yeah, we're gonna see them in a separate session, but let's go through the last problem of this chapter. Is it 1.7? Yeah. So now let's suppose that we have a positive integer. So n greater than 1. So n is a positive integer and is greater than 1. Now we want to prove that among n different integers. I want to prove that among n different integers, of which none are divisible by n, at least there are two that their difference is divisible by n. this one is running out. I can get some black markers for the next session. All right, so let's go through it. So we have an integer, positive integer n, which is greater than 1. And then we want to prove that if we have n different integers, which none of them are divisible by n, at least there are two within those like n different numbers that their difference is divisible by n. So now what we can do is let's consider those numbers because we have n numbers, right? Let's give them some like symbols. So we can consider those numbers are a subscript 1, a subscript 2, all the way till an. So a1, a2 till an, these are those numbers that none of which are divisible by n. And then if we use the division algorithm that we had, so we can find their, like, if we divide them by n, we can find their respective, like, quotient and remainders, right? So, for example, we can say that all these ai's can be written as, if we divide them by n, they're gonna have some qi, which is their quotient, plus some remainder, which is r subscript I. So instead of writing all of them one by one, we just write them in this general form, right? Instead of saying a1 equals nq1 plus r1 and a2 equals nq2 plus r2, we just write down ai and then nqi and ri. So these are all like respective like indices. And for all of them, because the remainder should be between 0 and absolute value of n, and n is already like positive, right? So this should be less than n. We don't need that absolute value anymore. And then instead of greater than or equal to 0, this should be greater than or equal 1. Why is that? Because we already assume that none of which are divisible by n, right? So in the case that r actually equals 0, we call the number or ai divisible by n because the remainder is 0. So when we know these numbers are not divisible, so at least we know they're not 0. So they start from 1 and they go up to less than n, which is absolute value of n. But if I want to write it as an inequality, because these are integers, right? So if a number is less than n, it means that is less than or equal n minus 1, just one number less than that, right? So now what happens is we have how many of these ai's or how many superscripts for I? I know my i's are changing, or I belongs to this group of all the way 1 to n, right? This is a subscript that I is allowed to take. So now if you look at these ai's or i's, we have n of them. But look at the remainders. The remainders should be chosen from a pool of numbers from 1 all the way to n minus 1. So now the amount of numbers, the number of numbers, there are actually one more the amount of remainders are allowed to take, right? So what happens based on the pigeonhole like theorem, that if you have 10 pigeons and then you have 9 like baskets and that they want to go in, at least 2 of those pigeons, at least there's a basket that has more than 1 pigeon, or like it has at least 2 pigeons, right? Because if you start with all of the baskets, put 1 pigeon in each of those baskets, then your 9 baskets gonna get full after adding 9 pigeons. So the 10th pigeon, when you want to go in, it has to go at least to one of them. That makes one of the baskets to at least have more than one. So in this case, we can decide based on the pigeonhole theorem that at least 2 of these are i's as well, because now the number of baskets are this n minus 1, the number of pigeons that they want to go is just actually n, right? So 2 of those pigeons have to go to the same place. So now we can say I can find 2 different indices because my I is going from 1 to all the way n. So I can say I can find 2 indices such as like I and j, which I and j are not equal. Like I'm not talking about the same exact indices, like one can be 1 and then the other one n. We can find 2 of those indices that this Ri equals Rj, because the remainder were the pigeons and the baskets were the numbers 1 to n minus 1. So at least two of those remainders are the same, right? So now if you consider the number ai minus aj, because now we're talking what, at least there are two numbers that they're difference, right? We found the indices. Now let's see how it applies to the numbers. So if we subtract those specific like ones that we have the remainders the same, what's gonna happen is ai gonna be it wasn't b, sorry, we're dividing by n. So it's gonna be nqi plus ri, then minus nqj minus rj, right? And then we know ri and rj are the same, so they cancel each other out. And then I'm left with nqi minus nqj. So if I take that n out or factor it out, we are left with this. So now their difference is actually can be written as n multiplied by a difference of two other integers, which are their quotient. So now based on this, we can say that n divides, or actually ai minus aj is a multiple of n. So now we prove that if we had n different numbers like ai's to n's, that none of which were divisible by n, at least two of them like this I and j are found there, that their difference is a multiple of n, or n divides that, right? So this was the last problem of the chapter, and then we have practice problem. There are 11 of them, and I'm gonna dedicate a separate session for that. So yeah, I hope you enjoyed it, and I'm looking forward to see you on the next session. Take care.